All right, so in this video, what we're going to look at is how a catalyst relates to activation energy and the difference between a homogeneous and a heterogeneous catalyst. We're going to see that they have very similar ways that they affect a reaction, right? They're going to make a reaction go faster, but we're going to see that the mechanism for how that happens is slightly different. So first, we're going to start with just looking at an overall reaction mechanism that we have for the basically decomposition of ozone, and this is without a catalyst. We're going to notice that we were not going to see a catalyst here. So we have our reactions, we have our rate laws that we can write here for this reaction mechanism. And just as a refresher, we can write our rate law. So rate 1 equals K1 times ozone concentration to the first order. And again, for with each of these reaction mechanism steps, each of them represent elementary reactions, so the order is equivalent to the coefficient. And again, we can only do that with our elementary steps. Our second step would be our rate equals K2, concentration of ozone, concentration of our original, this oxygen atom. And here what we can do is we can look at these and we see our K value is basically 0.2 for the first step, and our K value for the second step is 3 times 10 to the negative 7th, or 0.000000003. So it's a very small number. And so we see that can let us know that this is likely a faster step, and this would be our slower step. And so we see here, this step here, our second step, is going to be our rate limiting or rate determining step. And our slower step is going to restrict how fast our reaction can happen. Now we can look at our overall reaction, and our overall reaction is going to be where we have our intermediates cancel. And we see our oxygen atom here is our intermediate. It's produced in our first step and then consumed in our second step. The overall reaction would be 2 molecules of ozone going to 3 molecules of O2. And that's our overall reaction that we'd see with these two elementary steps. Now, what we're going to notice is that if a catalyst gets presented into this, we're going to see how does it affect our rate and why does it affect our rate. So a catalyst is going to lower the activation energy, or this barrier of potential energy that needs to be met, by providing another pathway for the same overall reaction. And in a reaction mechanism, a way that we can observe this is that a catalyst is a reactant or consumed initially and then produced in a later step. And we're going to see that this is basically the opposite of what we notice in an intermediate. An intermediate is something that is produced in an early step and then it is consumed in a later step. So we see the opposite thing happen. An intermediate is made along the way. A catalyst, we consume initially and then produce it again. The net effect of both of these is that the concentration of these two things, an intermediate or catalyst, does not change overall, nor are they represented in our overall reaction. So now if we look at our second mechanism that we have here, and this is the ozone reaction with a catalyst. And this is actually the reaction mechanism that was proposed that dealt with the ozone hole over Antarctica. And we'll see it's because of just these simple chlorine atoms that are present in the atmosphere way, way up there that we get this ozone hole being formed. And let's talk about why is this going to happen with regards to the reaction rate being faster? And so we'll notice here is that there's another step, but what we will see is that this other step is actually going to speed it up a little bit. So we still have the same first step. There's no difference here. But our second step, instead of just ozone reacting with an oxygen atom, now we're going to have ozone react with this chlorine atom. And this chlorine atom then produces O2, ClO, and then again we have our intermediate being consumed at a later step. And we also have another intermediate here, our ClO, being produced at another step. And then we also see that we have our catalyst being produced in a later step. So again, intermediate produced first, consumed later, a catalyst consumed first, and then produced later. Now what we see here is that this has drastically changed the rate constant values for these steps here. And because of that, this is now our slower step, and these two are our faster steps. But now what we see is that our rate constant value is a larger number in our slower step than it was in our original second step here in our first mechanism. And so because of that, we are going to have a faster, we could think of slow step, or a faster rate limiting step. And so we see here is that our K value has been changed, and we're going to observe, well, what is the reason for our K value changing? We're going to see it's going to deal with this idea of activation energy. But our reaction is going to happen faster now, and what we'll notice is because this pathway right here is a different reaction pathway than we had before. The pathway we had before, basically step 2 here has been replaced by step 2 and step 3 of our reaction mechanism in the second step. Now we've created a different path this can happen on, but we'll notice, let's see, do we get the same overall reaction? So our overall reaction is going to be an ozone molecule, another ozone molecule, and that's going to produce 1, 2, 3 oxygen molecules. And so we see here that our intermediate of the CLO molecule gets consumed, our intermediate of the oxygen atom gets consumed, and then our chlorine atom that we originally consumed gets produced later. So we notice that neither one of those are part of our overall reaction. So we have, if we look at this here, the same overall reaction. So we'll notice that is true for any time we add a catalyst. Adding a catalyst is not going to change what our reaction is. What a catalyst is going to do is it's going to provide a different pathway for that reaction to occur, which causes that reaction to happen a little bit faster. Now, this is kind of what we can observe it within regards to a reaction mechanism. So let's talk about how does a catalyst actually change a reaction and make it go faster. So we're going to look at this by looking at our activation energies. So here what we have, if we're going to do that, we want to look at a diagram of our potential energy with our reaction coordinate. And again, what we're going to do is we're going to look at how does this affect our reaction that we're going to see. And so what I'm going to do is I'm going to focus on simply the second step of mechanism 1 versus the second and third steps of mechanism 2. Okay, and actually let's go ahead and color code these a little bit different so we can see that how they may differ here. We're going to call this our second and third steps for mechanism 2. So if we have our second step is that we're going to have our reactants here, and this is going to be our, if we go over and look at our original second step that we had in the first mechanism, it's going to be O3 and oxygen atom, and it's going to have to go over some activation energy. And let's say this step we would observe is an exothermic step, and then we end up with 2 O2 molecules at the end of the day. So now we have this activation energy, and this is the activation energy without the addition of our catalyst. Well, now in our second reaction mechanism, we notice that what we've done is we've given it a different path, and we've made basically one elementary step into 2, but those 2 elementary steps have a much lower activation energy. And what we'll see is that we'll have our first step is going to be a lower step, but we'll see, we notice something kind of weird here, and that we actually end up with 2 kind of humps almost, where we have, this would be right here, the activation energy for the second step of mechanism 2. So that would be the process of our catalyst being added in now. If we go back up here and just zoom in, we'll see that this is the process of our ozone reacting with this chlorine atom. And so that's our second step. And then we would also have, we didn't go down all the way back down, but now this right here would be the activation energy of our third step. And so what we see is that we've reduced the activation energy that is needed for this process to go along. And the reason for that is that now what we've done here is that this would be our Cl plus ozone step. And our third step is going to be our ClO plus an oxygen atom step. But the overall net effect is that we still start with our ozone and an oxygen atom, and we end up with 2 O2 molecules at the end of the day between our second step of reaction mechanism 1 and our second and third step of reaction mechanism 2. And so because of this, we see that the activation energy with the catalyst is smaller. What we'll notice is that it's going to increase the K value. Now, how does it increase the K value? Bring us back to the Arrhenius equation. Our frequency factor e to the negative EA over RT. What we've done is we've decreased that activation energy for that first part of this two-step mechanism that we observed for our second mechanism. And because of that, that's going to increase the K value that we would observe. And that higher K value is going to make our rate happen a little bit faster. So again, now if we're looking at this, our mechanism shows that when we add a catalyst, it gives us a different path. We don't follow this same path anymore. We now have this two-step path that we would observe where we're first going to react with our catalyst, have our first step happen, and then our second step where we're going to have that product that was made with that catalyst react with that oxygen atom. But the net effect is that we get the same overall reaction that's happening. Again, our second step for reaction mechanism reaction mechanism 1 was O3 plus O goes to O2 plus O2 effectively. And then our second and third step, so we look at our second step for our reaction mechanism 2. This is O3 plus Cl goes to ClO plus O2. And then our third step is our ClO plus our oxygen atom to give us Cl and O2 again. And so what we see here is the overall reaction that we're observing between this different pathway that we get is the same. Our intermediates go away, our chlorine atoms that are catalysts go away in our overall step here, but we still have O3 plus an oxygen atom to give us 1, 2, 1, 2 oxygen molecules. And so we see again, it's the same reaction, the same reactants and products. What we notice is that all that's happening here is we've given it a different pathway, and that different reaction pathway has a lowered activation energy, which allows our reaction to happen much faster. So hopefully we have an idea of how catalyst works, how it actually leads to a faster reaction, and that has a direct consequence of the fact that it has a different path, and that different path has a lower activation energy.